that's fine. Okay, I'm using S sub k because they represent series formulas, like what we did in the warm-up. So it's like I already did all the work, and I'm telling you that the sum of k terms is whatever 6 divided by k plus 2 is. And all we want to practice is, what is the sum of an extra term, k plus 1 terms? So notice that all I'm changing in my notation is my subscript. Instead of having k, I have k plus 1. So that means in my formula, wherever I see k, I sub in k plus 1. So I would say S sub k plus 1 is 6 over, and then I would do k plus 1 where k is, but of course I still have to add 2 to it. Now, I do like to protect it with parentheses so that if I need the parentheses, I have them. There's nothing to distribute or no exponent, so I don't really have to worry about it. I can go ahead and add in the denominator. That's 6 over k plus 3. So the sum of k terms is 6 over k plus 2. The sum of k plus 1 terms is 6 over k plus 3. And this is what we're going to be looking for in our proof so we know we're done. If we can get to 6 over k plus 3, we'll have made our proof. I'm going to do this one. S sub k equals 3 over k times k plus 4. And we're just going to find S sub k plus 1. So again, all I'm really doing here is changing the subscript, which means that where I see k, I should write k plus 1. And that would be for all the k's. So I now have multiple k's. No k in the numerator, so it stays 3. But in the denominator, this first k, I'm going to protect it. It's being multiplied, so I'm going to put it with parentheses, k plus 1. That first k became k plus 1. Okay. And then sometimes, I'm going to do a little bit of work here in my head. I'm going to put k plus 1 in for this second k, and k plus 1 plus 4 is so the sum of k plus 1 terms is going to turn into 3 divided by k plus 1 times k plus 5. I don't ever multiply those out. You could write k squared plus 6k plus 5, but I just, like if I get something that's a trinomial in my algebra, I just factor it, and then it should equal s sub k plus 1. So I use factoring. All right, and then I've got 2 more, and then I'll let you do some practice. So let's let S sub k equal k squared over k minus 3. I'm going to do S sub k plus 1, which all it's asking me to do is make a substitution for k. So that'll be k plus 1 quantity squared over, and then whenever I have one that's just adding and subtracting, I'll just k plus 1 minus 3 is k minus 2. I can do that adding and subtracting together in my head. I don't do k plus 1 times k plus 1 in the numerator. You could. It's k squared plus 2k plus 1. But like I said, if I get to a trinomial in my numerator, I'll just factor it, and it should be k plus 1 quantity squared. Okay. S sub k plus 1 for this last one. 3k times k minus 4 all over 4 times k plus 1 quantity squared. You just go through every single k in that formula needs to be turned into a k plus 1. So I've got a 3 times k, but now I'm going to put k plus 1, so I'll protect it with parentheses. And then in that next set of parentheses, k minus 4, if I put in a k plus 1, that'll be k plus 1 minus 4, which will be k minus 3. It's just going up by 1, right? That adding and subtracting there, as long as there's no coefficient to k. And then in the denominator, I'll have 4 times the quantity k plus 2 squared. Because k plus 1 plus 1 is k plus 2. And I don't have to multiply those things out. Yes, you could distribute the 3 to k plus 1 and get 3k plus 3. You could FOIL that out, but you don't have to. Okay, you can just use factoring in your algebra. Okay? You try these 6 problems. They are from the textbook, so if you're having trouble at your groups, I know like at the back pod, sometimes the board is hard to see. If you can't see them, they're on page 642, and it's numbers 5 through 10. Okay. The book is going to give you a P sub K. That's fine. If you want to change it to S sub K, that's totally cool. I'm just using S sub K because we're going to be doing series formulas, so they are going to be S's. And they want you to find P sub K plus 1 for all of those. So I'm going to give you 5 minutes. And after 5 minutes is up, then I'm going to show you the answers. So you'll be able to check and see if you did it okay. Remember, I don't like FOIL stuff out. So I just like sub in, do any kind of little simplifying that I can, and then I'm good. And let me know if you have a question while you're working. I moved too fast if you're confused by my K plus 1. Because that one might be harder for you to like keep factoring, but once I get like the in from these simplified, then I'm good. Careful on this. So it is 2K plus 2. That's right in front of my face. Be careful with number 8. That's probably, I think, maybe the tricky one for today. I'll put it on the board and I'll put my answer up there here in just a little bit for all of them. Talk about that too. Okay, here are the answers on the board. So you can check them. Remember, I do like simplify within the parentheses, but I don't do any like foiling with individual parentheses. I do want to talk about 8 as you're checking. So 8 is P sub K equals K divided by 3 times the quantity 2K plus 1. And when I sub in the k plus 1 for all those k's, you know, you're putting k plus 1 in, and it's getting multiplied by 2. So that would distribute to both parts of that k plus 1. So through distribution, this becomes 2k plus 2. And then there's still a plus 1 out there. So 8 comes out to be k plus 1 over 3 times 2k plus 3. If you have the plus 2 on number 8, you didn't distribute. When you sub in your k plus 1, all of k is getting multiplied by 2. So all of k plus 1 gets multiplied by 2. So you got to distribute that. That's probably one of those that's like easy to miss. So like if you have distribution, maybe write it down like in the margins of your paper. It will be really frustrating if you get your k plus 1 statement incorrect, because then you're trying to like prove something that isn't right, and that's not going to work out. Okay, so you want to make sure that you have the correct S sub k plus 1 statement. Does anybody have any questions on any of the others? Okay, let's get into mathematical induction. Okay, I'm going to skip around here. I'm going to talk about the big idea of mathematical induction and how this proof works. It's different than like the arguments you made in two-column proofs in geometry, where you just like had to like find all the things, like the angle pairs or side pairs, and like once you got angle, side angle, then you have this thing, and it all like followed really nicely, and you have a reason for everything. What you're kind of creating here with mathematical induction is something called the domino effect. So like, if you've ever set up dominoes to make like a really cool display, you like line them up just perfectly, right, with enough space in between them, so that when you kind of kick over that first domino, all the other dominoes fall. A really important part of mathematical proof is that you've proven something in all cases. Well, it's really hard to prove in all cases, you know, like by plugging numbers in. Maybe it's impossible to prove all cases by plugging numbers in, because you'd be going to infinity, and you don't have time for that, right? So the domino effect says, let's first prove that the first domino falls over. So like, let's prove that the first case is actually true. Okay. And then let's prove that the k knocks over the k plus 1 domino. So it doesn't matter what k is, k always knocks over k plus 1. If k is 1, then that's 1 and 2, or 2 and 3, or 3 and 4, or 4 and 5, or 5 and 6. And so what we're saying is we always knock over the next domino. We've knocked over the first. There they all go. We've proven it in all cases. So it's super useful if it works. Okay. Knock down the first domino and the rest will fall. You don't have to write this slide down. Okay. I'm going to kind of talk about it in terms of steps, and then I'm going to put it like more specific to what we're going to do here in chapter 9. Okay. So this is like the general idea of the principle of mathematical induction. You can read in the textbook if you want to look at this again. Okay. You'll have some statement, like they're calling it a P sub n. We're going to be doing S sub n's because all of ours are going to be series formulas. Okay. And we're basically going to do those two steps that I just described with the dominoes. We're going to show that for the base step that P sub 1 is true, that this actually works when n equals 1. Okay, so we'll like sub in n equals 1, we'll get an answer back out, and we'll say like, yes, this is the thing. Okay, so we'll prove that the first domino falls over. Then the main work of our proof is proving that the k and the k plus 1, or k implies k plus 1. So that's your induction step. For every positive integer k, so you're letting n equal k now, which is kind of weird because it's like, why would I make another variable equal another variable? Okay, so we're just saying like, we can sub in any positive integer k for n. And when we do that, P sub k implies that P sub k plus 1 is also true. So that's one domino knocking over the next domino. And it doesn't matter which number dominoes they are, they always fall. Okay? So if we've knocked over the first, and then we show that successive dominoes knock each other over, then we can make this statement at the end that it's true for all. So here's going to be our setup for series formulas. Okay. And I'm going to fill this in with like some like formula stuff, and it's going to be a lot like sequences in series. So over here on the sideboard, I'm just going to write like a reminder to us from 9.1 to 9.3. A sub n is the nth term of the sequence. And S sub n is the sum of n terms. Series. Just so that you can kind of keep track of all those notations. Okay, so like when I'm working on mathematical induction proof, to make sure I have all the parts that I need, I kind of remember these 5 like pieces over on the left. You're going to sound like a really fancy mathematician today. When mathematicians want to like start talking about something that they want to prove, they often use the word let. So you're just like, let this be the thing I want to tell you about today. What we're going to fill in after let is our S sub n. So we're going to say let S sub n, the sum of n terms, be the first term plus the second term plus the third term plus dot, dot, dot. Who knows how many terms we're adding until we get to the nth term. So we're just adding up individually all the terms. And then we're going to say that equals a formula in terms of n. Because that's the thing that we're trying to prove, that this formula actually works. So like in the warm-up, I did that one with like n over 2 times 4n minus 26. So like that could be our formula at the end of it. Okay, so that's just you being a mathematician and telling everybody what it is you're investigating. Okay. All right, step 1. This is what I call the base step. And this is when you let n equal 1. Side note. Okay, so step 1 is letting n equal 1. So we're going to do S sub 1 equals. Okay. You're going to actually plug 1 in for n. So make that substitution. Work it out in this formula, like whatever it is. And then show that it's true. So I usually just say something like, which is true. And like it will depend on what formula you're proving. We're doing series formulas, so we're adding up terms in a sequence. S sub 1 is trying to say the sum of the first term. Well, the sum of the first term is just the first term. So what we should see when we plug 1 in for n in the formula and we work it all out is that it'll equal this a sub 1. And as long as it does, then we've proven the first domino false. Okay, so S sub n, S sub 1, and now we're going to get to, before we get into actually step 2, we're going to do an assume. And when I assume, I let n equal k. So it's like some positive integer k. We're going to use integers because we're doing series, so we only have like first, second, third, fourth terms, not 3.5 terms. So basically, I go up to my let statement, and everywhere that I have an n, I write a k. So I assume that S sub k is a sub 1 plus a sub 2 plus a sub 3 plus dot, 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 a sub k equals, now it's a formula in terms of k. So I always try to tell people, like, in that assumption, don't make that hard. All you're really doing is copying down your first line with K's instead of N's. Now, what that means is we're assuming that thing to be true, so that K terms actually adds up to that formula in terms of K. What we want to do is show that if K works, K plus 1 also works, right? So that's our show that statement. That's when we do the stuff we practice at the beginning of class. We're going to just see what S sub K plus 1 should come out to be. Like, this is going to tell me, like, when I stop my proof. When I get to this formula algebraically, I've proven it. Okay. So we're going to show that S sub K plus 1 equals, and then you plug K plus 1 into your formula that you assume to be true. So it's going to be like a new formula, just like we were practicing at the beginning of class. So you use the assume, this formula. You just put K plus 1 in for K. You simplify. This is what you're trying to prove. The end of your proof, right here, if you can get there. Okay, step 2. Do the work for S sub K plus 1. So that means, like, I've done my assumption. I know what I'm trying to prove for S sub K plus 1. I actually have to do the work for S sub K plus 1. Which is asking for a sum of K plus 1 terms. So I would start at the first term, and I would add the second and the third, and even the K term, right? It's kind of like I'm copying my assume. I'd add up all those terms. But if I stop at A sub K, that's only the Kth term. And I'm trying to do S sub K plus 1. So this is where, like, I got to create this. I've got to find the next term, which would be A sub K plus 1. Okay, so I'm going to put this one in red, plus A sub K plus 1. So that one, you're going to have to do a little bit of work for. We didn't practice finding A sub K plus 1s, but it's essentially the same idea as S sub K plus 1s, right? You know what A sub K is right before it. Plug in K plus 1 and work it out. I'm also going to show you a little cheat for that. This is the K plus 1 term. But that's like all the long work I would do to add up the sum of K plus 1 terms, right? Add up all the terms. Okay, so you'll show that setup every time. You'll have to do the red stuff. You have to figure out what that is. Okay, that's on you. You gotta find that red thing. But notice, we assumed something to be true. That A sub 1 plus A sub 2 plus A sub 3 plus A sub K, all that stuff in black before my new term, K plus 1, that was equal to that formula. So you'll be able to make a substitution. Substitute the formula for S sub K. All those terms will disappear. They'll come down to one simple formula. We assumed it to be true, so we can make that substitution. Which means the next line will be S sub K plus A sub K plus 1. So instead of having all those things get added together, you're really only adding two things. The formula for K terms and the extra k plus 1 term that you would be adding to it. And then, this is the really fun part, do the algebra until you get to s of k plus 1, or your show that statement. So I'm going to say, do the algebra until you get to your show that. Because remember you said, show that s sub k plus 1 is this new formula. I'll add these two things together doing any algebra I need to do. There's usually probably like 4 or 5 steps. And then it'll be that thing I said show that for. And I'll close it with a thus s sub n is true. You can say thus, therefore, hence, whatever makes you feel most fancy. Okay. Okay, so that's kind of like the outline or the framework that will work for all of our proofs. I'm going to do one with you now. I'm going to follow these steps, so keep looking back up here and see how I'm getting my different steps. And then your job is to try number 11 tonight. Okay. Okay, when you look in the textbook, you're going to see something that looks like this. Please don't write it down right now. It's going to say, like, prove this thing. Okay, so it says prove that 6 plus 11 plus 16 plus 21, and then it put the rule for a sub n, that was all equal to this formula. So it's kind of like what we did in the warm-up. We, like, made up a formula using Gauss's rule for arithmetic. Tell everybody what you're working on. So start your proof with let. Okay. And we're going to let s sub n equal, and you just copy down the problem from the book. Okay, so it's always going to give you all that stuff. Number 11. You just copy down that stuff after that. So let s sub n equal 6 plus 11 plus 16 plus 21 plus dot 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 5n plus 1, and that equals n times 5n plus 7 all over 2. So all I did was add the word let and then s sub n to that proof statement. All right, after our let statement, we're going to knock over the first domino. So I'm going to do the first step, which is show s sub 1 works. And that's show the formula works. So we're going to plug 1 in for n in this formula over here. Okay? We don't want to plug it in for the sequence. We're trying to prove this formula works. So let's see. Let's replace all the n's with 1. So that would be, what, 5 times 1, which is 5 plus 7 all over 2. I do a little bit of work right there. That's 12 over 2, which is 6. And notice in the sequence, the first term is 6 in the series. So the sum of the first term would be 6. So we can say, oh yeah, which is true. Like anyone looking at that can see that the sum of the first term is 6. And it'll always work out. I'm asking you to prove things that are true. Okay, then we've done the first step. We're going to get ready for induction, so we're going to make an assumption now. We're going to assume that this works for all k's. So we're going to let n equal k. It's really a matter of like copying this down, but replacing all the n's with k's. So we're going to assume s of k is 6 plus 11 plus 16 plus 21. Here's my first substitution, 5k plus 1, because I changed my n to a k, and that equals, here's my next substitutions, k times 5k plus 7 all over 2. I didn't do any math other than a substitution. So I let n equal k. Okay. If we assume that to be true, then we want to show that s sub k plus 1 equals, and you just have to figure out what the k plus 1 statement is. So you go to this formula over here at the side, and I'm just doing my work off on my margin. That's k plus 1 times 5 times k plus 1 plus 7 all over 2. I would distribute my 5, so that's k plus 1 times 5k plus 5 plus 7 all over 2, right? So then that's 5k plus 12. So I want to show that k plus 1 times 5k plus 12 all over 2. If I can get to that answer in algebra, I've made my proof, because I'm showing that s sub k implies s sub k plus 1 is true. Okay. So that stuff in blue is what you practiced at the beginning of class. Okay. All right, step 2. Here's the meat of your proof. Now I actually have to do the work. So this is where you really start doing actual work and thinking things out. So I'm going to start with s sub k plus 1. I'm going to add up k plus 1 terms, which would start with 6 plus 11 plus 16 plus 21 plus dot dot dot, and I would get to 5k plus 1. But remember, that's just your a sub k. And I need to add on that new term. That's my a sub k plus 1. Like I need to add an extra term onto it. So I'm not just adding k terms, I'm adding k plus 1. Okay, there's different ways you can get k plus 1. This is what I'm going to call the long way. If a sub k is 5k plus 1, then a sub k plus 1 is 5 times k plus 1 plus 1. Distribute 5k plus 5 plus 1, 5k plus 6. It's just kind of like the same stuff I did with s sub k and s sub k plus 1. I just make the substitution and simplify it. Here's what I call the short way using patterns. 6 plus 5 is 11. 11 plus 5 is 16. 16 plus 5 is 21. 5k plus 1 plus 5 is 5k plus 6. Ooh, I like that way. Either way works. Okay. So like that one, 5k plus 6, you got to think of that. That's your job. Add that extra term. It wasn't there before. Okay. All right, now compare. Look at the thing you assumed. 6 plus 11 plus 16 plus 21 plus 5k plus 1. All of that simplifies to be this formula. We assume that to be true. So 6 plus 11 plus 21 plus 5k plus 1. All of that equals k times 5k plus 7 all over 2. All those terms added up, the sum of k terms, we have already assumed to be true by the formula. And we just have to add 5k plus 6. Because we need an extra term. Okay, in order to, like this doesn't look like my show that statement. So now this is where I'm just doing algebra. In order to add these, what do I need? common denominators. So I'm going to multiply this one by 2. So that's really like 5k squared plus 7k over 2 plus 10k plus 12 over 2. And now they have the same denominators. I did a little bit of distribution. But I can add across. That's 5k squared plus 17k plus 12 all over 2. Okay, so I combined them. And I look back up at my show that. It still doesn't look exactly like my show that statement, but I have a trinomial. To make it look like my show that statement, let's just factor it. And hint, hint, it should factor to be k plus 1 times 5k plus 12, right? So let me just write it like that. Hang on one second, okay? I'm going to write it like that. 5k plus 12 times k plus 1 over 2. FOIL it out. 5k squared plus 5k plus 12k. There's my 17k plus 12. It is actually that thing. So thus it is true. Okay, please remember, I want you to try number 11. Try setting it up, the let statement, S sub 1, try the assume, try the show that, and get as far in the algebra as you can.